Welcome to today's deep dive. We're looking at a really comprehensive 2026 industry report today on the current state of quantum computing.
Yeah, it is a massive document.
It really is. And our mission today is to just cut right through all the tech jargon. We want to explore how quantum computing has, officially crossed that threshold from theoretical physics experiments to scalable real-world engineering.
Right.
We're going to break down exactly why 2026 is the undeniable inflection point for this tech and what it actually means for your digital life.
Because it really is a watershed moment. I mean, the industry has finally moved away from the whole hype cycle.
Thank goodness.
Yeah, they're completely focused on demonstrable utility now and fault-tolerant architectures. We're seeing this fundamental transition in how these systems are built from the ground up.
Okay, let's unpack this, because for the past decade, the industry was completely obsessed with horizontal scaling.
Essentially just cramming more and more physical qubits onto these messy two-dimensional grids.
Right, which created massive heating and wiring bottlenecks.
Yeah.
But now, they've shifted to vertical scaling. They're using 3D chip integration to solve those physical constraints and just keep everything cleanly connected.
And what's fascinating here is how this shift plays out in the real world with Google's Willow chip.
Oh yeah, the Willow chip.
It's a huge milestone. The chip uses an array of 105 fluxonium qubits.
Which is a specific type of superconducting circuit, right?
Right, one that's designed to be highly resistant to noise. So it ran the quantum echoes algorithm, and to put the computational acceleration in perspective here, it completed a calculation in under 5 minutes that would theoretically take the world's fastest supercomputers 10 septillion years.
Wait, 10 septillion years down to 5 minutes?
Exactly. That is a 13,000-fold speed up.
Wow.
But the real breakthrough is the stability. Willow hit 10 billion error correction cycles.
With zero logical failures.
Zero.
Zero logical failures across 10 billion cycles is just a huge leap in stability. But how does that actually compare to what competitors like IBM are doing?
Well, IBM is taking a completely different hardware philosophy. They're going highly modular.
Using those low-density parity check codes.
Or LDPC codes, yeah. Because of this approach, they actually require 90% fewer physical qubits to create a stable, error-free logical qubit. Both methods are just making massive leaps right now.
So what does this all mean for you and the broader economy? Are we seeing actual returns on investment yet?
We absolutely are. Take pharmaceutical giant Roche. They recently used quantum simulations to identify 3 viable Alzheimer's drug candidates in just 18 months.
And historically, that process takes 4 to 6 years.
Right. And in logistics, the Port of Los Angeles is using quantum optimization to shrink their complex routing calculations from several days down to just 50 minutes.
That's incredible.
And if we connect this to the bigger picture, the environmental implications are just as profound. Right now, generative AI has a massive global energy drain.
It's consuming around 1,050 terawatt hours globally.
Yeah. Quantum computing offers a highly sustainable computational alternative for these massive optimization tasks.
But wait, don't quantum computers require those massive supercooled refrigerators? How is that actually saving energy compared to AI?
That's a great question. While AI requires these power-hungry GPU farms just to crunch numbers, the quantum processor itself draws incredibly little power.
Oh, I see.
The main energy cost is simply keeping the system cold near absolute zero, which is still a fraction of what traditional data centers consume. The catch, however, is that this extreme refrigeration relies on helium-3.
Which is pretty rare.
It's ecologically sensitive and incredibly rare. It requires careful management as the industry scales up.
Okay, here's where it gets really interesting, because as this technology matures, we are facing a cryptographic ticking clock.
Right.
Adversaries are actively using a strategy right now called harvest now, decrypt later.
Basically, bad actors are stockpiling your encrypted data today.
Knowing they can't read it yet.
Exactly, but with the explicit intent of breaking it tomorrow when fault-tolerant quantum computers are fully online.
And that is why the report stresses that 2026 is the non-negotiable deadline for global PQC migration.
Post-quantum cryptography.
Right. NIST has finalized the new cryptographic standards, and organizations must transition to these frameworks immediately to prevent a digital security crisis.
It's not a future problem. The execution year is right now.
So quantum technology isn't some far-off sci-fi concept anymore. It's already here.
It is.
It's actively accelerating life-saving medicine, optimizing global supply chains, and forcing a mandatory high-stakes reboot of the entire internet security infrastructure.
Which raises an important question. We're watching nations aggressively race for sovereign quantum capabilities.
While international groups like UNESCO struggle to bridge a growing global quantum divide.
Between those who have this tech and those who don't. So consider this.
Yeah.
If a nation secretly achieves fault-tolerant quantum decryption tomorrow, would you or the rest of the world even know your data was compromised before it was entirely too late?